Okay, so your midsem is coming up fast, right? In this explainer, we're going to connect all the dots from your syllabus. The goal here is to turn that long list of topics into one single story, something that's actually going to stick with you on exam day. So let's just dive right in. I get it. You look at the syllabus, and it's easy to feel like you're just staring at this mountain of totally disconnected topics. You've got data standards over here, deep learning over there. But trust me, it all fits together. And this explainer, think of it as your roadmap. All right, here's how we're going to tackle this. 4 parts. We'll start with the messy problem of health data. Then we'll see how NLP helps us make sense of it. After that, we'll watch these tools work in a real-world algorithm. And we'll finish up with a super quick recap to get you ready to ace that exam. Okay, section 1. Let's start at the very beginning with the core problem. Health data is just chaotic. And if we want computers to make any sense of it, we absolutely need rules. We need standards. So think about it. A patient's record is this wild mix of stuff. You've got your structured data, lab results, vital signs, the kind of thing computers can process pretty easily. But the real clinical gold, the juicy details, are all buried in the unstructured text. We're talking about a doctor's notes, a discharge summary. Getting computers to understand both of those, that's the whole game in health informatics. The solution here is this big word, interoperability. And you can think of it like a 4-step ladder. First, you've got the technical level. Can the systems even connect to each other? Then comes syntactic. Can they read the data's format? Like, can they parse the file? But the real magic, the goal, is semantic interoperability. This is where systems actually understand the shared meaning of the data. And the final step on that ladder is process, which is when that shared understanding actually makes a difference in a real clinical workflow. Right, so semantic interoperability, that's the holy grail. It's not enough to just send a file from one place to another. The system on the other end has to know that a specific ICD code and the text unspecified asthma are talking about the exact same thing. And that's precisely why standards like SNOMED CT are so essential. They act like a shared dictionary for all of healthcare. Now, SNOMED CT is pretty clever in how it handles complexity. It does it in 2 ways. For simple stuff, you just use one pre-coordinated code. Bam, pneumonia, done. But for more complex ideas, you use post-coordination. This is where you combine multiple codes. So you would take the code for pneumonia, add the code for caused by, and then the code for streptococcus. It gives you both simplicity and this incredible expressive power. And hey, this pre versus post-coordination thing, it's a classic exam topic, so make sure you lock this one in. Okay, so we've got these standards for creating shared meaning. That's great. But how do we even find a concept like pneumonia buried inside a doctor's messy, free text note to begin with? Well, that's where natural language processing, or NLP, comes into play. The first attempts to get computers to understand words were pretty basic. Take one-hot encoding, for example. It basically creates this gigantic list, a vector, for every single word in the dictionary. It puts a 1 at that word's spot and zeros literally everywhere else. The result? It's huge, it's mostly empty or sparse, and worst of all, it has zero concept of meaning. The vector for asthma is just as different from pneumonia as it is from the word car. There's just no sense of any relationship. The big breakthrough came from this really simple but incredibly powerful idea called the distributional hypothesis. It's summed up by this great quote: "You shall know a word by the company it keeps." Basically, a word's meaning isn't in the word itself, it's in the words that surround it. Words that hang out in similar contexts, like doctor and physician, probably have similar meanings. And this idea, it's the foundation for all modern word embeddings. So Word2Vec is what puts that idea into practice. And it does it in 2 main ways. You've got the CBOW model, which stands for continuous bag of words. It takes the context, like patient presented with severe blank, and tries to predict the word in the middle, maybe asthma. Then there's skipgram, which does the complete opposite. It takes the word asthma and tries to predict its likely neighbors. Either way, what you get are these dense little packages of numbers, these vectors, that actually capture the meaning and relationships between words. But here's the thing, context is everything. A general-purpose model like BERT, which was trained on, say, all of Wikipedia, just doesn't speak the language of medicine. It doesn't know the lingo. That's why domain-specific models like BioBERT, which was pre-trained on tons of biomedical articles, are so incredibly powerful. You can see it right here in the numbers. The performance gains are huge. And it's all because BioBERT just has a much better grasp on the company that biomedical words keep. All right, so let's recap where we are. We've got standards to create a shared meaning, and we've got NLP to pull that meaning out of raw text. Now, let's put it all together. Let's see how this stuff actually powers real-world research by building what's called a phenotype algorithm. So why should you care about all this? Well, look at this number right here. When researchers tried to find patients with rheumatoid arthritis using just structured data like billing codes, they only found about 51% of them. But when they added NLP to read the doctor's notes, their success rate jumped up by 12%. We're talking about thousands of patients who would have been completely missed otherwise. That's a massive deal that can completely change the power and the outcome of a study. And this isn't just some random guesswork. There are really rigorous processes for this, like the I2B2 methodology. The idea is you start really broad. You pull in anyone who might have the condition. Then you narrow it down using both your structured data and your NLP variables. But the crucial step, the most important one, is you create a gold standard training set by having human experts manually review a bunch of patient charts. Only then do you build and test your algorithm against that human verified truth. It's a really systematic and scientifically defensible way to do it. So a key metric you'll hear about is PPV, or positive predictive value. It answers a really simple but vital question. Of all the patients my algorithm said have the disease, how many of them actually have it? This is super important, especially for expensive stuff like genetic studies. You need a really high PPV. We're talking over 90%, because you absolutely cannot afford to waste time and money on patients who are misclassified. Okay, we've walked through the whole story, from chaos to clarity. Now for what might be the most important part of this whole thing, the rapid-fire recap to make sure you absolutely nail this exam. Let's hit the key facts and, more importantly, the common traps you need to avoid. All right, listen up, because these are the classic trip-ups on exams. First, FAIR does not stand for Fair, Flexible, Authenticated, Interactive, Responsive. Don't fall for it. Second, an ontology is a directed graph, but it can have cycles. That's a key distinction. Third, in the FHIR standard, a profile is mandatory to constrain a resource, even if the URL isn't. And finally, remember what we said about SNOMED CT? Post-coordination uses multiple concept IDs, not just one. You need to know these cold. So if that's not what FAIR stands for, what is it? It's findable, accessible, interoperable, and reusable. Simple as that. These 4 principles are basically the foundation of modern data sharing. I would absolutely expect a question on this. All right, quick facts on the old-school HL7 standard. It's basically a text file. Each line is a segment, and the fields inside those segments are separated by those pipe characters. But if you remember one thing, remember this. The first segment of any HL7 message is always the MSH, which stands for message header. Always. And finally, here's the cold, hard math for why we need standards in the first place. If you try to connect n different systems without a shared language, the number of point-to-point connections you have to build is calculated with this formula: n times n minus 1, all divided by 2. The point is, the number of connections just explodes exponentially. It becomes a total mess. A central standard, like FHIR or SNOMED, is what prevents that chaos. And that's it. We've gone through the entire pipeline, from the initial messy data to the standards in NLP that give it structure, all the way to the powerful algorithms we can build on top of it. See? These aren't just a random list of topics from your syllabus. They're a logical chain. You've seen how all the pieces connect. You've got this. Now go ace that exam.